Sodium borohydride and lithium aluminum hydride are both reducing agents. The difference between the two is lithium aluminum hydride is the stronger of them. The dividing line in strengths occurs between ketones and esters. Above this line, sodium borohydride can reduce, like aldehydes. Sodium borohydride, presence of ethanol, will change an aldehyde to a primary alcohol. It'll change a ketone into a secondary alcohol. Now, this particular secondary alcohol, it's chiral. Since it's chiral and the starting material is not, and nothing here is optically active, this is actually a racemic mixture of both enantiomers. Now, these two reactions can also be used with lithium aluminum hydride. Lithium aluminum hydride is much stronger than sodium borohydride. Lithium aluminum hydride is so strong that you cannot use it in the presence of a protic acid because your protic solvent would react with lithium aluminum hydride instead of a carbonyl. Here, sodium borohydride will react with an aldehyde and a ketone faster than it will with ethanol. Therefore, you can use sodium borohydride in the presence of a protic solvent. Lithium aluminum hydride is different. You have to use a aprotic solvent, such as ether, first. And then once all the carbonyls have been reduced, you have a sort of an acid workup step to supply the proton. Esters, carboxylic acids, and amides are not readily reduced by sodium borohydride. Instead, you really have to use the two-step procedure of lithium aluminum hydride in ether, followed by an acid workup step. In the case of an ester, you end up cleaving this bond right here, and the acid workup step provides this H and this H. The hydride provides the hydrogens that attack the carbon. With a carboxylic acid, you have a very similar result, except the carboxylic acid is reduced to a primary alcohol using lithium aluminum hydride and H3O+. Amides, for an amide, basically the carbonyl is removed altogether and it's replaced with two hydrogens from the lithium aluminum hydride. Now, this is actually a three-step procedure. First step involves lithium aluminum hydride in ether. Second step is the acid workup step that accompanies a lithium aluminum hydride reaction. Now, thing is, this molecule right here, it's an amine, so it's basic. So there's a third step. Because you have an acid step and a base step, you have to add in a base reaction to free your basic molecule out. So when it comes to reducing amides to amines, you need to have that third step right there. Where you would differentiate the two is where you have say an aldehyde and an ester. You want to selectively reduce the aldehyde. The way to do this is use the weaker of the two, sodium borohydride and ethanol, as this normally doesn't have the strength to attack an ester. If you wanted to reduce them both, you would just use lithium aluminum hydride.